Where we left off last time, I showed you this reasoning that we can use, where if you start with a polynomial, we can assume there's an integer root, and we can move the constant term to the other side. That lets us factor out a k, and then we can divide by k, assuming it's not equal to 0. On the left-hand side, we see it must be an integer. Therefore, the right-hand side, because it's equal, must also be an integer. And that restricts the range of things that k might possibly be, because we know for the right-hand side to be an integer, it must evenly divide 99. So that's the logic. Let's try and generalize this into a theorem, not about this particular problem, but about any polynomial. All right, so if we want this to apply to any polynomial, we're going to go through those same steps, only we're not going to start with a specific equation. We're going to write down the form of a general polynomial. So if you haven't seen this before, the idea is you have a constant, which is just a number, it's a coefficient, times x to the n. And then you can add something that's one smaller. So a to the n minus 1 is just another number, and then x to the n minus 1. So let's do this. I'll show you a specific example of this in a second. So a1 times x to the first power, a0 times x to the 0. Anything to the 0 power is just 1, so I'm not going to include an x there. So this is the usual way to write a general polynomial. Just as an example, let's pretend n equals 7. So we'd have some number times x to the 7th, because n is 7. Then we'd have a different number times x to the, 7 minus 1 is 6, so x to the 6th. And then you'd have a 5th degree term and a 4th degree and so on, all the way down to a number times x plus a number equals 0. So this is how you're more used to thinking about polynomials, with specific numerical coefficients and decreasing powers of x. And this is just a general way of notating that kind of idea. So if this is our general polynomial, let's try and do the same reasoning. By the time we get to the end, you'll see that there are some other conditions that will need to be true up here, but let's wait until we discover them to write them. So we're going to say if k is an integer solution, we know that if you plug k in, the equation should still be satisfied. Try and imagine, what were the next steps that we took? And if you want to pause the video and actually try and do the steps from before, I think that would be a great exercise. So the next thing that we did was we moved the constant term to the other side. Then what we did was we factored a k out of all these terms. And just a note there, if I have n k's, so I have k times itself n times, and I take away one of those k's because I factored it out, now I have n minus 1 k's left over. So this factoring out, each of the exponents should decrease by 1. All right, next we divided by k. Last, we observed that the left-hand side must be an integer. Therefore, the right-hand side must be an integer. Therefore, k must evenly divide whatever this constant term at the end of the polynomial was. So k has to divide a sub 0. Okay, so this is pretty good, but it doesn't quite work yet because there's a couple of small conditions that we need to write down that would make this proof invalid. So one of the things that we did was we divided by k, and we know that if you divide by k equals 0, that would produce an undefined result. So we could say if k is an integer solution not equal to 0, equivalently, we could say that a sub 0 doesn't equal 0. Either one would be okay. So let's do this. If k is an integer solution not equal to 0. There's another important condition, though. Imagine that one of these coefficients was the square root of 2. So let's say that this second coefficient was square root of 2. This entire argument wouldn't work. Think about where exactly it would go wrong. Which step of the logic would fail if that coefficient was actually the square root of 2? Where it would go wrong is in this very last concluding step. So we'd said the left-hand side is an integer, therefore the right-hand side also must be an integer. But if one of these coefficients is square root 2, then I'd have square root 2 times an integer, And if you add that to a bunch of integers, the left-hand side is no longer an integer. So an important condition is that all the coefficients up here must be integers. So let's add that as a condition for our proof to be valid. So now you can see up here I've added with integer coefficients. The last thing is that usually if you write a general polynomial in this form, each of these constants is a real number, but there's nothing saying that it's not 0. Like I could have like 5x to the 7th plus 0x to the 6th plus 0x to the 5th all the way down to just 4. So in that case, we still have all these middle terms. It's just that the coefficients are 0. So the last thing that we typically do is we have some statement that says that at least one of these coefficients isn't 0, or I think it would be nice for this one to just say that if we're going all the way up to degree n, that this leading coefficient isn't 0, because it would be weird. And there's the bell. So it would be weird to have like a quadratic equation and say my quadratic equation is 0x to the 7th plus 0x to the 6th all the way down to 2x squared plus 3x plus 1. So let's also say and an not equal to 0. Okay, so now we've got all of our conditions. We've got the logic. We've got the conclusion. So that's the proof of the integer root theorem. Come back next time and we'll see how we can generalize this to be a little bit more useful and conclude things about rational roots rather than just integer roots.